Okay, so let's do another problem. This time, let's move away from math, which is a little bit boring. Let's do a physical problem. Let's imagine you have a bar, an L-shaped bar. And there's a force, which can be represented by a vector, let's say in this direction. Let's call it F. Okay? So we'll set up a coordinate system, let's say centered right here. This is my Y, this is my bar, this is going to be my X. Let's say we have a given force F, which I decide to draw from this particular point. Let's call this point A. And let's call the center of my coordinate system O. Let's say that my force F has a magnitude of 2 and is being defined with an angle of 45 with respect to the positive x to make our life simpler. And let's imagine that the dimension of my bar are 2 in height and 3. So this is 3 and this is 2. So I'm going to plot another vector which I will call vector r. So this vector starts at point O and ends at point A. Now I'm sorry, I'll apologize, my diagram is obviously not correct. R appears to be parallel to F, but they're not. Okay, we need to trust the dimension. So this is trusted, this is trusted, this is given, this is given. Okay? So again, I repeat, F and R are not parallel. I would like to calculate R cross F. So, for me to calculate this, first I need to figure out whether it's clockwise or counterclockwise. Second, I need to figure out its magnitude. If I would like to use the standard definition of RF sine theta, I need to figure out the angle between R and F. Obviously in this problem, that's going to take us a bunch of steps. Because first we need to figure out the angle between R and X, and then we need to play around with this angle and 45 to figure out the exact angle between R and F. Everybody agrees? Then once we got this, we need to figure out the length of R, which we can do using Pythagorean theorem, but that sounds like at least 3 or 4 steps. If you see this, stay away from this method. You should go right away with the matrix method. So for us to be able to use the matrix or determinant method, the first thing we need to do is write both vectors in component notation. And the advantage of this, it's child play, it's super easy. The x component of R is 3, the j component of R is 2, and then the x component of f is 2 times square root of 2 over 2, which is square root of 2, and the y is the same. Okay? And then I can set up my matrix. I, j, k, 0, 0, 3, 2, square root of 2, square root of 2. And if I calculate the determinant of this, I confirm that I and j are 0, and k would be 3 times square root of 2 minus 2 times square root of 2. Therefore, my final answer would be square root of 2k. Okay? Fast and easy. That's usually the method that people use when they have a hard time visualizing in which direction the torque is going to go. And again, this will be the method that most likely you will have to use in three-dimensional space. Okay? Let's try to redo the exact same problem with the conventional method. Remember, I'm going to switch board now. Remember, the conventional method was to figure out, so let's say my R is 3, 2, and then my f is whatever. Let's pick 30. Let's change the angle, and the magnitude is the same. Remember, you can either expect to figure out the perpendicular component of r with respect to f, or the perpendicular component of f with respect to r. Let's do both of them. This component of r is my r, let's call it parallel. This is my f parallel. This is my r perpendicular, and this is my f perpendicular. Okay, so I'm decomposing two vectors the same way as we've been doing it last week. Now I know that if I do the cross product between each term, then I'm going to have to do r parallel cross f parallel plus r parallel cross f perpendicular plus r perpendicular cross f parallel, and so on and so forth. 4 terms, right? But you know that the cross product between two parallel component and two perpendicular component will give you 0. So the only one left are going to be r parallel cross f perpendicular. That's this guy. And you should not forget that maybe there might be a component of the torque which is given by r perpendicular cross f parallel. Let's look at, and that's this guy. So this is a case where you need both. So let's look at each individual case. First term is going to be the cross product between this guy, let me use another color, this guy, and this guy. So if r is going like this and f is going up, what is going to be the direction of this cross product? Is it going to be clockwise or counterclockwise? Anybody? R, what is the direction of the first term? R parallel cross f perpendicular. Counterclockwise, yep. What is going to be the direction of the second term? R perpendicular and f parallel. This is r perpendicular, and then we're going to cross it with f parallel. Exactly. Obviously, the direction is clockwise. So this is a particular case where one vector cross another vector is not obviously in one direction versus the other. It all depends on the magnitude of this term and the magnitude of this term. If the magnitude of the second term is bigger than the first one, then the overall will be clockwise, and therefore negative. If the first term is bigger than the second term, then the overall will be counterclockwise. So keep in mind that the torque created by two vectors, as you decompose them with the horizontal and perpendicular, will not always give you two terms both in the same direction. Sometimes one term might be in one direction, the other term might be in the other. How are you going to know which overall direction it is? You don't know unless you calculate the magnitude of each term. And if you do it that way, it's sometimes easy to forget one of those two terms. What if you do the matrix? Both terms will be given to you as you calculate the determinant. This minus this times this. This product is going to be one term, and this product will be the other term. So the advantage of the matrix is you can never forget one term, especially when the direction is not that clear. Okay? So again, please practice both methods. You know, whenever you have a vector across another vector and you're not able to use the angle between the two, you know, you have to use the component, but you're too lazy to use the matrix yet, you want to try to figure out by yourself, you know, practice this. Decompose your r and your f in both x and y, and then cross the parallel of one with the perpendicular of the other one, and then vice versa, the perpendicular of one with the parallel of the other one. And then set up the full matrix and confirm your results. You will see as you practice that you will spend way less time by expressing each component in each vector in component notation and filling up the matrix automatically, rather than trying to figure out if it's going to be clockwise and counterclockwise and work out each term independently. Okay? So again, please use both methods, but at some point, make sure you practice the matrix method, because this will be helpful in 3D.